Now, once the question is well defined in one's mind, one has to proceed to obtain the answer to that question, and there are a few steps a scientist takes, and this is what I will enumerate now. The most important and and most prevalent method of answering a question is to formulate a hypothesis. Okay. So, the first thing that one does is to propose and test a hypothesis. A hypothesis is essentially a scientific guess. It is a scientific guess, and the way to answer mainly how did it happen kind of question is to propose hypothesis and test a hypothesis. And this is almost a mainstay of science. Almost all science is built on proposing and testing hypothesis, and therefore, I will spend separate lectures on that. So, in today's lecture I am not focusing on proposing and testing hypothesis, because more lectures will be needed for that. But effectively the point is that if a question is there in the scientist's mind, in order to answer the question, the scientist guesses an answer, and that answer, that guess answer is the hypothesis. The hypothesis needs to be scientific, and there are certain criteria for the hypothesis to be scientific. I will come to that later. And then one has to test the hypothesis. Remember, I mean, look back to the time when I was dealing with the philosophy and logic. I said that if you start from a premise and use deductive logic, and you arrive at something that is deductively obtained from this premise, if the premise is wrong, the deduction would be wrong, the result will be wrong. If the premise is right, the result will be right, provided the deduction is correct, that means it is valid deduction. But if it is wrong, if the premise is wrong, still the deduction can be correct. I have shown that, right. So, one can arrive at a true deduction starting from a wrong premise. Now, how do we test hypothesis? Essentially, from the hypothesis that we make, we obtain by applying deductive logic certain experimentally testable prediction, and then we test it. Okay. So, when we have tested this, when you have tested the hypothesis, actually we have tested some experimentally testable prediction from the hypothesis, and which means that we have applied the logical structure that we have already done in this course. Starting from a premise, apply logical structure, obtain a result. That is what we are testing. If the result is tested experimentally to be false, then the starting premise is false, and that provides a way of eliminating hypothesis. But otherwise, we cannot say that a test becoming correct is directly meaning that the hypothesis was correct, and so one has to keep on testing further. I will come to details of this issue a little later. The second thing a scientist does is to propose and test postulates, or I will write postulates. Postulates are also scientific guesses, but postulates are scientific guesses regarding a law of nature. This is something that always happens. While a hypothesis can be regarding a particular event, how did it happen kind of a question, postulates are related to how does it happen kind of question. which means that these are related to laws of nature. Let me give an example. When faced with the question, how do all the planets move in particular ways, elliptical orbits with the central body and the focus, how does it happen? Newton guessed that it happens because any two bodies attract each other with a force, force equal to G m1 m2 by r square. It was a guess, but then he said, he showed that if this guess is true, if this assumption is true, then I can show why, I can mathematically prove that the orbit of planets should be the way they are. So, when a scientist proposes a postulate, what is his statement? The statement is that I am making a guess, I am making an assumption, but if I make that assumption, then I can show that that is true, what is actually observed. So, in making a postulate, the scientist takes a shot at some law of nature, that is, law of nature means something that is universally applicable, not to any particular body, it is that is universally applicable, and he says that if I assume that, then I can show that that should happen. For example, when it was a quandary why the atoms are stable, the electrons by the law of electromagnetism are supposed to spiral into the nucleus and supposed to fall into the nucleus, but they are not falling. The things around us are stable. How does that happen? And Niels Bohr made the postulate that electrons can occupy only specific levels, specific orbits. And only when an electron makes a transition from one orbit to another, either it absorbs energy, a specific amount of energy, or it releases a specific amount of energy. So, that was his postulate. He would say, if I express his point correctly, he would say that I do not know why this is true, but if I assume that, then I can show why what is observed is observed. That is the character of a postulate. When people could not explain various phenomena in the micro world, most important being the black body radiation curve that I talked about in one of the earlier classes. Then the idea of quantum mechanics developed. Also the problems concerned the stability of atoms, the problems concerned why do particular orbits are there the way Bohr postulated, why are these. So, you can try to obtain some kind of another postulate whose consequence will be a postulate that was postulated earlier. In fact, that is what happened in quantum mechanics. So, the quantum mechanics people, those who developed quantum mechanics between 1925 to 27, short span of time, but practically the whole edifice of quantum mechanics was developed in this period. They said that let us assume that the state of any particle is completely given by a complex number psi. It was a postulate. The scientists would say, I do not know why that happens, I do not know why it is true, but if I assume that, then I can show this. Then they said that whatever are the observables we can observe, like the position, momentum, energy and things like that, those are represented by operators, mathematical operators. It is a postulate. The scientists would say, I do not know why this happens, but if I assume that, I can show this. Then they said that what we can actually observe in an experiment are the eigenvalues of these operators. Postulate. There is no reason to believe why it should be so, but they say that if I assume that, postulate that, then I can show why the nature behaves the way it does. So, that is the character of postulates. In postulates, we are taking a shot, a guess at a law of nature, but these postulates have no explanation by themselves. These are assumptions, but the scientist says if I make that assumption, then I can explain why this happens. That is the character of the postulate. So, the scientist's main activity are proposing and testing hypothesis and proposing and testing postulates. The third one, measuring a constant or a parameter. Measurement, and most of the tests of hypothesis or postulate involve measurements, and so measurement is a very important activity in science, and I will come to again a separate set of lectures on the issues involved in measurement. In measurement is essentially you need to have something that is measurable in the first place, something which can be ultimately converted into a number, and that number has to be measured, and that number then is used as a test of a hypothesis or a postulate or to understand something in nature. How far is the earth from the sun is a major measurement problem, was for a long time a major measurement problem, because there is no way to no direct way to measure it, cannot be measured by parallax. I have already illustrated, told you what parallax is, but the distance between earth and the sun cannot be done that way, because the stars behind the sun cannot be seen, and therefore, the parallax cannot be measured. So, that constituted a problem for a long time. So, measurement is a very important activity in science. Once you have done a measurement, then we try to construct theories out of it. And the way to construct theories, for example, I have a question regarding a phenomenon where there are certain variables, and I do not know how this variable affect that variable, and so on and so forth. So, I perform an experiment, and that indicates that there is a functional relationship between two variables, and that prompts us to develop a theory. So, measurement often leads to certain functional relationships between variables. So, that is another activity, important activity that we do, establishing a functional relationship. The functional relationship is always between a independent variable and a dependent variable. So, whenever we are investigating a phenomenon, within that we try to identify what is an independent variable which can be independently varied. That means, the experimenter has the ability to vary that independently of other things, and other parameters vary as dependent on that. So, these are the dependent variables or parameters. Often it is found that there is a dependent variable and an independent variable, but the dependent variable is dependent not only on one variable, but many. So, if you want, then suppose Z depends on x and y, then in order to obtain the functional dependence, we have to keep y constant first, vary x and see the variation in z, then keep x constant, vary y and observe the variation in z, and then combining these informations, we can find out how z depends on these variables. But we can definitely state that if x, y is constant, then z depends on x in a particular way. The Boyle's law, Charles' law are established exactly that way. One thing is kept constant, the other thing varies. So, the way to obtain these functional dependencies involve plotting graphs, getting a best fit graph, get best fit plot, because the points will be scattered, they will have errors. One has to get a best fit curve, and that then fit that curve to some kind of a functional form. How to do that? We will come to that again in a later lecture. How to obtain the functional dependence. For example, it's easier to find a linear functional relationship. It is relatively more difficult to obtain a nonlinear functional relationship, because various nonlinear functions would tend to satisfy a particular variation. So, we normally either we try to obtain a linear relationship or a power law relationship, which can be obtained by drawing a log plot. We will come to that later. So, establishing a functional relationship. Once we have established a functional relationship, then that prompts theoretical thinking. One can think, why is this functional relationship true? This is exactly what happened in case of the black body radiation. People ask, why is this true? Or one can have a prior theoretical basis which told us that a functional relationship should be linear, but doing the experiment you can fit the linear curve and find out the slope of that line, thereby extracting a parameter which again is fed into the theoretical work. So, the theory and experiment actually go hand in hand. After one goes through this process of establishing a functional relationship, one has to develop a mathematical model. Developing a mathematical model of physical phenomena. Physical means not only coming from physics, but all fields of science, even social science. Developing a mathematical model is a very fruitful, important activity, because that enables prediction. If you have a mathematical model, not only just a causal relationship stated as a sentence, but also a mathematical functional relationship, then if something happens, what is going to happen, that can be predicted and that can be tested. So, the way to go forward in science is therefore to develop mathematical models of the things that we see around us. And mathematical models often, even mathematical models in biological systems often lead to certain insights into the biological phenomena. Not only insights, but opens ways of investigation into biological phenomena, which would be impossible if the mathematical model were not built. And so, building a mathematical model is a very important scientific activity that we engage in all the time. Finally, this is somewhat rare, but still there, seeking something new. Well, that is what the scientist does all the time, but this is in the early days people were all the time seeking something new, but now most of the things are explored, and therefore, we can seek something new only when we develop a new apparatus, a new way of doing something that was not possible before. For example, when Galileo first invented the telescope, he looked at the sky without any premonition about what he is going to see, and he saw things. He was looking for something new, and he saw things that are new. He saw the satellites of Jupiter, phases of Venus, and so on and so forth. When the 200-inch Mount Wilson observatory was built, large telescope was built, Edwin Hubble looked at the distant galaxies and looking for something new, and he found something new. When people first developed the way of cooling something to very close to absolute zero, then people started wondering what can you see at this temperature, something new. This something new can be explored only if you develop a technique, develop an apparatus to do something that was not possible before. And today the particle fields are building bigger and bigger particle colliders, stronger and stronger with larger energy. Why? Because then by colliding particles they are seeing what is new, they are trying to see what is new. So, seeking something new is still possible, but consequent to your developing something, some ability, some way of exploring material world in a new way, then only it is possible.